I wanted to do a few examples for problems in Chapter 32. You have those due Monday. At least in the 2022 year, they're due Monday. And I know some people are at the musical. So I'm going through 3 different examples here. Actually, the second one is the most painful of them. And I did not assign something quite that bad. But it's still helpful to see. So this is a drawing. It's problem 22 at the end of the chapter. And you've got a current I2 of 12 amps here, a current of I1 of 18 amps out here, and an unknown current of I3. And it says that the flux is 1.38 times 10 to the negative 5th Tesla meters. And it's asking you what direction and magnitude is the current I3. So we have something like this. We have something like this as our formula. So that is the flux over there on the left side. You don't need to evaluate that line integral. It's given to you. Vacuum permeability, 4 pi times 10 to the negative 7th, and then the net current. Well, since this is going around clockwise, if you use your right-hand curvy hand rule, that tells us the positive direction is pointing into the page. Well, since this is coming out of the page, and we have a positive flux over here, that tells me that I3 is definitely going to be into the page. And in fact, the net current into the page is 11 amps. So since the net current is 11 amps, and right now I have 12 amps pointing out of the page, I3 would have to be 23 amps pointing into the page. I1 doesn't matter at all because it's outside the bound area, not something we're concerned with. If I look at this, I'm going to go to problem 68 because I think it's more like the ones that we would have. In this case, you've got 2 springs, and they're holding onto a wire that's going vertically here. And there's a 20 centimeter block of magnetic field that's 0.5 Tesla. And essentially then, what you're trying to figure out is if the current is going down like that, and you know this magnitude of magnetic field, you're trying to figure out the amount of that current. So essentially these springs compress by 1 centimeter. They each have a spring constant of 10 newtons per meter. So I want to think about balanced forces. And there's several ways we could think of balanced forces with this type of problem. This one is spring forces compared to magnetic forces. So in this particular case, we've got magnetic to the left, 2 springs acting to the right. Why are the springs acting to the right? Because they're compressed to the left, therefore they're pushing to the right. So I could say magnetic force is equal to spring force, BIL equals 2K times delta X. So that's Hooke's law over here. And I know 0.5 Tesla, I, 0.2 meters, 10 newtons per meter, 0.01 meters. So the current is going to be 2 amps down. Now one thing it didn't say here is what is the direction of the field? Well, if the field is basically causing a force to the left and the current is going down, then that means the magnetic field is coming out of the page. I don't think it asked that, but it's something that I think should be noted. Magnetic field would be pointing out of the page. And I use my right-hand rule for that because we think of conventional current. So I've got the fingers pointing into the page. The current would be going down, and therefore the force would be to the right. So now if I have the fingers pointing out of the page, finger pointing down, my force is to the left, and that's what agrees with the free body diagram. So therefore the magnetic field has to be pointing out of the page. If I go back up here, this basically has an electron that's shot across a 10 kilovolt potential difference into an area. And of course, did I mention this? No, I did not because I'm an idiot. I believe it is a 2 centimeter wide area. So, hey, guess what I'm going to do? I'm going to show that now. 2 centimeters. Don't need that italicized. Don't need it bolded. Let's make it purple so that in the future no one will notice what a screw up I was with this. Ugh. Perfect. Nobody will know. At any rate, so that's 2 centimeters across there. And it says at the end of that, it's deflecting at 10 degrees. And it's asking what strength of field will deflect that electron by 10 degrees. So there's a lot going on here. I mean, I know essentially there's going to be a magnetic force acting on it. I do realize at first I'm going to have to figure out the speed of this electron as it enters the field. So to think about that, I'm thinking about it as an energy problem. The electric potential energy is going to be converted to kinetic energy. So electric potential energy is Q delta V. Charge in an electron is something you should know. It told you it was 10 kilovolts, that's 10,000 volts. So it's that many joules. Convert that to kinetic energy, and I get this electron, and this is the mass of an electron, and that's something you should pretty much know as well. So the speed of this is 5.93 times 10 to the 7th meters per second. That is very fast. That's well over 10% the speed of light, probably about 20% the speed of light. So we might even start to get some relativistic effects there. At any rate, the next thing I need to do is if it's going that fast, I need to figure out how much time it's going to take to cross this. So I can use a very simple formula. V is equal to delta x over t, so t is equal to delta x over v. I know that distance is 2 centimeters because it's been there forever, and the speed horizontally. So I get 3.37 times 10 to the negative 10th seconds to cross that. So the next thing I want to think about is I need to find the vertical velocity that this is going to have at the end here to get that 10-degree angle. The next two steps could have been done in different order. So basically, I'm going to use trigonometry, and I'm going to draw a triangle here. That's my horizontal velocity. That's going to end up being my vertical velocity to get a 10-degree angle. So VV is equal to that times tangent of 10 degrees. It's about 1.05 times 10 to the 7th meters per second vertically. So the next thing we need to do is figure out, well, what acceleration do we need to get this vertical velocity in this amount of time? Well, acceleration is dv dt. 1.05 times 10 to the 7th meters per second divided by those seconds gives me that acceleration. And that is a ridiculously high acceleration, but for electrons, that's not that ridiculous. I said ridiculous instead of ridiculous. That in itself is ridiculous. As you can tell, it's kind of late at night. I've just enjoyed the spring musical Rent. Nice job, Ellie. So the next thing, and I thought it was last, so I was going to say finally, and it's fifth because I had to do something else. So once I know the acceleration, I need to find the force. So to do that, I need to use Newton's second law. Comes out to 2.83 times 10 to the negative 14th newtons. Now I'm going to find the magnetic field strength. Using magnetic force as QVB, I'm going to use my horizontal velocity here because that's going to end up telling me the magnetic force. So in this particular case, I've got that force on it that's magnetic. I just figured that out. I know the charge on the electron. I know the speed that it's ending up moving. So I get around 3 times 10 to the negative 3 Tesla. Now maybe, I think that's it. So that's a 6-step problem. That's a tough problem. I don't think any of the steps are particularly difficult. The toughest one might be this first one where you're realizing you need to find electric potential energy to find the kinetic energy of the thing. After that, it's really mostly a kinematics problem, right? In fact, the only other part that's E&M is that last step where you're finding the magnetic field strength. So hopefully those give you some idea of how to solve the types of problems. Thank you.